So hi folks, hi everyone. So I think we can start officially this seminar. So thank you all for joining us today. For this talk for the IGCP648 virtual seminar series. I'm Luc Doucet, so I'm your host tonight for those who don't know me. So for today's talk, we are having Dr. Max Rohrman, the Head of Geoscience at DECAN Geosolutions, presenting methodology for evaluating the North Atlantic Igneous Province reveals multiple hotspots at breakups. So it's about large igneous provinces, so I'm already very excited about the talk. Max, thank you very much for being here tonight, and the audience is all yours.
Okay, well, thanks so much for having me. Yeah, I'm just gonna talk a bit about a project I did a little while ago, which is about evaluating the North Atlantic Igneous Provinces, and I'm gonna look at basically hotspots and breakup. Obviously, the North Atlantic is a very famous area, and lots of work have already been done. So what's the reason actually why I'm doing this? So this is sort of the organization of the talk. I'm basically looking at, I'm interested in excess mantle potential temperatures, like delta TP, and using the geological record as a proxy for magmatic productivity. So first I'll go into an introduction about large igneous provinces and breakup. Then I'll go into a data methodology section, where I sort of look at Iceland and the whole Atlantic margin back to basic to breakup. Then looking into a stratigraphic correlation of the basalt stacks, and also looking at the significance of unconformities. And that's especially important when we're looking at variations in mantle potential, excess potential mantle temperatures. Further on, I'll look at trace element geochemistry to get information for delta TP from mantle melting models. And I'll look at seismic velocity, P-wave velocity, also to gain excess potential temperature information derived from mantle problems. Furthermore, I'll look at magmatic crustal thickness estimation, so that basically the thickness of new magmatic crust being generated, which normally is like the lower crust and the basalt stack. And then I'll look a bit at volcanic transport directions and compare that with current models that are in the literature. Finally, I'll look at the different melting parameters, so potential temperature, active mantle, upwelling here with G, and fertile mantle and other variables, and make sort of a new model for the North Atlantic Igneous Province formations. And then there's some conclusions. This is sort of the classical sort of stuff that you've probably seen in literature for many years now. Mantle plumes, you know, are thought to have happened in the Atlantic about 60 million years ago, when Greenland and Europe are still close together. Lots of volcanism was produced, and people postulate this huge plume that was flattened about 1,200 kilometer diameter, coming from potentially the mantle, the core mantle boundary. On the other hand, there is like, so this is one sort of set of models are all plume based. Another set of models are more rift based, and basically based on Mackenzie stretching. And if you then heat up the asthenosphere, then you can actually generate lots of magmatism. And that was sort of the idea of White and Mackenzie. You got a mantle plume, and then you get rifting, and sort of the rifting generates all the excess magmatism. There's a couple of sort of issues with that. If you look at non-volcanic margins, then you got the nice sort of, you know, tilted fault blocks dipping towards the center. But if we look at volcanic margins, that's actually not the case. You've got these huge stacks of seaward dipping reflectors, here with SDR. And they're actually, the faults are dipping towards the continent, and not so much as in the non-volcanic margins where they dip towards it. So that's a bit peculiar. If you want to, you like this model, then why does this actually happen? Why do you have these big stacks, and why they're dipping the different directions? So that's why I sort of leave it at. I'll now go into what I'm actually going to talk about in this particular study. So we'll look at the North Atlantic, and then basically go to all these points that I'm sort of pointed out over here. You can read them for yourself. So this is the North Atlantic. Greenland sits over here in the west. There's the UK there, Norway, and Iceland sits here in the middle. In red and yellow are various hotspot tracks calculated by using hotspot models, either fixed or moving. And basically in green here are magnetic highs, basically. And this one is very famous. This is the Greenland-Iceland-Faroe Ridge that stretches all the way from eastern Greenland to the Faroe Islands, which sits over here. Similar sort of things can also be detected near the Vuring basins, but it's much more sort of vague, and the Iceland ridge is much more visible. All the black lines in here are seismic refraction lines, which I go into to some extent. There's the Yamayan microcontinent, which is largely below sea level here in purple outline. And of course, there's the Reykjanes Ridge over here, the Kobainsee Ridge towards the north, and then the Mohns Ridge further up. I will look at sections here in central eastern Greenland, here with this blue polygon, and also in the Faroe Islands. And there's some studies in the past from Larsen about 20 years ago that say that these two areas must have been very close together, less than 150 kilometers apart. There are huge outcrops, about 6 kilometers of basalts over here and in central east Greenland, and they have been correlated. And that's pretty important if you want to know where actually Iceland or the whole Greenland-Iceland-Faroe Ridge sort of started from. Also in these circles over here are commercial wells, most of them, but some of them are also ODP wells, like here on Sigma 3, and here on the Vuring margin, ODP642E. And I'll talk a little bit about them later on as well. So we'll start off with the central eastern Greenland section and the Faroe East section over here. In green is the pre-rift sequence, and then there's all these interesting names, nonsense formation. It's not so important for now, but more important is to recognize that green is pre-breakup and purple is sim breakup. And you can see here from the ages, which are all argon-argon ages, that the whole section, this is about 6 kilometers here, probably was deposited in 1 million years or around that time. Also important are these unconformities. There's this A unconformity, which can be correlated from Greenland to the Faroe Islands, labeled A here. And there's another one called C. One thing about the flows to know is as well that there's a high titanium flows, which is about more than 1.5 titanium oxide. And there's low flows, which are here in dark purple, which are below 1.5 titanium dioxide percentage. So this picture here is from the Faroes on a nice sunny day. Oh, clearly not, because there's always bad weather there. Basically, you see the difference between the pre-breakup, the Biosphere formation, which is over here. And this is the A unconformity over there. And then this is the sim breakup section, the Mount Studur formation, which sits over here. And this unconformity is quite important, and I will sort of go into that a bit more in detail. A long time ago, 20 years ago, Tegner did actually a section of basically the Greenland section, and he looked at titanium, magnesium, and also these DIYB and LASM ratios, which you can plot in this plot here. And basically, so this is the Greenland plot. So you see here these light purple plots is basically the Milne Land and Geikie Plateau formation, which you can see here as well. So basically what you see here from 1.6 to say 1.4 is basically this section over here. Then the younger section, the upper portion, is here in blue, are these ones, the Skryne-Ternia and the Roma Fjord formation. And the green ones are not on this picture because he only looked at the section above and not below. But if you look at the section below the unconformity in the Faroe Islands, then you see they have very low DIYB values. And there's a big gap between the top of or the base of the Milne Land formation and the top of the Beinisfjord formation. And a recent study here by Millet has gone into these in a bit more detail, and you can see that there is probably a temperature difference and potential temperature difference. Actually, I'll explain this plot a little bit more. So basically, you see P solidus over here to the right, and then there's P segregation to the left. So basically, this is, if you look at the diagram on the left, P solidus is where they hit the solidus, and the P segregation is basically where it sort of hits where the geotherm comes out. So basically, the base of the lithosphere, generally speaking. These red numbers are ages, so 60, 59, and the red path is basically the path that sort of goes on if you go up in the section. So this is the oldest section, and then you basically go up till here. This is the percentage F of melting, 10% over here, 5%, 2% over there, and these are the potential temperatures. This is about 200 over here, about 100 over there. Also, you see here the Iceland field in light blue, and here some explanation for what you see in the reason delta TP is that way. So in this case, we have an increase in delta TP. Lithospheric thinning is more characteristic for the pre-rift section, which is going down over here. And then there's other factors like source depletion, which I'm not going into so much in this case. So basically here is what you see, or what's sort of happening from what you can sort of deduct from this picture. At about 60 million years ago, probably the lithosphere was about 100 kilometers thick. It thinned to about 75 kilometers, as you can see here from the segregation. Basically going from the Garnet field into the Spinel fields. Then basically there was another thinning event here 57 million years ago, which is over here, up to basically this point. So basically you thin this, the section even more from about 75 to probably around 60. And that's when the breakup unconformity, the BU, got formed at the base of this section. So basically there's lots of magmatism. There's a little bit of magmatism early on, 60 million years ago. Then it sort of increases a bit more. Then there's actually a stop when BU is. So basically we're going from here to there. So basically here sort of when magmatism stops at the unconformity, and then it sort of increases a bit again because of an increase in temperature about 56 million years to 55 million years ago. So these high titanium is sort of basically the deep melting, and the low titanium is the shallow melting. And this diagram actually more depicts the high titanium melting. So before I go into sort of the model, it's important to know something about seaward dipping reflectors. That's basically the seismic reflectors that you see off the margins. Basically, here's sort of a picture. They sort of tilt one way, but we know that they probably must have been horizontal and initially have flowed the other way around, as you can see in this picture. So if you go all the way back, in, let's say, a million years time, it must have flowed like that and then subsided and sort of tilted towards the ocean. There's two sort of flows. There's a landward flows and there's the lava delta. And this lava delta is kind of important because it gives you information about how the sediments run off. So it gives you the coastline and the direction of the volcanism as it hit the water or the seawater. And these, you can do some stacks with this. So how the hyoclastites, the lava delta, are sort of being built out as the shoreline develops. So this is probably a bit complicated picture, but basically you've got East Greenland, you got the seaward dipping reflectors are dipping towards the ocean, like you see over here. These are some pictures from eastern Greenland. And you can also see dipping dikes, which are basically sort of dipping as the basalt stack sort of evolves. So basically, initially they were all basically deposited horizontally. And then with time, the basalt stack sort of dipped down. Each new set of dikes is vertical again. So you basically get a slight sort of bending of the formation. On the Faroe section, it's the same thing, although it's actually dipping the other way around. And that is what's sort of depicted in these two pictures over here. So initially, the basalt stack in the pre-rift in green again, and then the syn rift in light purple, was basically just building up. There was probably a stop in volcanism here at the BU or the A unconformity, and then there was another here at C. But basically, as you go in through time, which is this arrow over here, basically the basalt stack was sort of building up, and you can see from the basalt in the field that they were actually all subaerial. So basically they were just building up, basically a big plateau, and basically you had all these unconformities like sort of labeled over here. And so why was that? It was a high temperature at that time, and so basically the mantle provided support, thermal support, to keep this whole stack, which was probably about 20 kilometer thick or something like that, above sea level, and you basically had a big volcanic plateau. So over here at the top, you see the temperature sort of distribution from the rare earth elements, the rare earth geochemistry, basically this dip at the unconformity, and then an increase, and basically all this syn rift volcanism here in purple. Now, after the last formation, basically there was an erosion event, and basically this whole section started to tilt more rapidly. That's because there was, at this MU event, which is the magmatic unconformity, there was another dip in the mantle temperature, which is sort of depicted here, right? It's yellow instead of the red. That means that the mantle could not support this big crustal section anymore, and it basically started to tilt down. But magmatism perked up after that, so the rift collapsed, but more magmatism sort of filled in the gap. And as this also sort of signifies the onset of spreading, basically you basically create a gap, and basically the section gets filled up as you go along. So that's basically what's depicted over here, and that's this massive unconformity. So you got basically the new sediments, or the basically basalts, are horizontal, while the older ones are tilted, and your hotspot tracks basically is going that way. You can still see a little bit of Greenland over here, but as the ridge, the Greenland-Iceland-Faroe Ridge develops, basically you get more of these sort of steps that there's basically a hiatus in the mantle temperature that creates basically a sort of makes it more likely for a ridge jump, and so basically the magmatism fills up the holes as you go along. So basically the whole rift, the whole Greenland-Iceland-Faroe Ridge is sort of created that in that way. This is sort of the time steps from the literature. So there's time steps 33 million years ago. There's 115, 7, 40, 52, and I tried to incorporate it. So basically, if you go back, you have Iceland basically sitting in Greenland and the Faroe Islands, and basically it opens up as you go along, which is in stark contrast, obviously, with mantle plumes coming from Greenland, because that's probably not really what happened. That's basically just calculated with not really that much evidence towards it. Most of these models use some of the evidence, like the ages of the basalts, but leave other evidence out, and then come up to these models. And in this magnetic picture, you can see that it's actually a much simpler solution if you just close it like that than having plumes coming from Greenland. So we're looking at this Greenland-Iceland-Faroe Ridge a bit better. There's a couple of seismic refraction lines, sigma 1, ice melt on Iceland itself, and there's the fire line. Sigma, ice melt, and fire line over here. And this is sort of the depicted geometries of the basalts here, which comes from a publication from Hjartarson over here. And basically they state that you follow the model which is developed by Palmeson. The ridge basically is basically over here. All the basalts sort of dip towards the rift and basically fill up unless there's a ridge jump, which is probably created by the dip in temperature that creates this unconformity and then sort of starts basically generating somewhere else. So this is sort of basically the record of all the ridge jumps. The problem with the sigma and the fire offshore is that we don't know exactly where those ridge jumps are. There are a couple of them, like 33, 50 million years, 40 million years, but there might be others that we're missing out. But you can sort of depict them where we have the synclinal structures, because they actually depict the rift. So there must be one here, which is the 33 one. The one at 40 is a bit less clear, but there's definitely also one. And you can obviously see the current rift over here. But there might be other ones depending on the problem is that the seismic is not very excellent, so some of them might be left out, and that's probably for future studies to see where they exactly are. But as a sort of first order approach, this is sort of what it looks like. Yeah. Oops, a bit too fast there. Okay, sorry about that. So now we can use magmatic thickness, which is depicted in age, and VP diagrams, which is the P wave velocities of the lower igneous crust for the Iceland hotspot tag, and look at the mean velocities and the thickness of the crust at that particular section. So this is the breakup. This is at the thickness at breakup is close to 30 kilometers. High mean VP, and you can sort of use three different sort of approaches. Basically, if you have a higher temperature, a higher delta TP, then basically you get a higher mean velocity, P wave velocity. If the P wave velocity stays sort of similar, then you probably have active mantle upwelling, while your age is going up, and then fertile mantle is sort of going in between. This goes basically, it's sort of a negative correlation from normal oceanic crust, which is here depicted in black. So high is 1 is basically passive upwelling, and the higher values are more active upwelling. So this is where you volcanic passive margins here in blue. This is where you would expect them to be sort of plotting along. And if there's any mantle involvement, you would expect them to be going towards the right in this diagram. You see some changes here. Although most of the Greenland-Iceland-Faroe Ridge sits about here, there are some steps that in the present day especially are much higher thicknesses, which is a bit peculiar, because then you would think that it would be huge active upwelling. But there's also another explanation for that, which is that there could be parts of continental crust which lower those velocities present, so that these velocities probably sit here, but the presence of continental crust makes it sort of thicker and looks like it's lots of active upwelling. Well, it probably is not really there. And there's some evidence from isotopes that there is actually old continental crust in parts of Iceland. So using this approach, we can go all the way back to breakup, which is where BU sits. Then the magmatic unconformity sits somewhere over here, about 54 million years. And then you can sort of step your way further using the unconformities as the step where you mantle potential temperature is low, is less than sort of 50 degrees. And you can also plot spreading rate here in green, gray on top of it. And it looks like that initially when the temperature was coming down in the early phases of the rift, the spreading rates were also going down, but about sort of 45, 43 million years ago, it looks like the spreading rate doesn't really keep track anymore with the drops in magmatic temperatures for the Greenland-Iceland-Faroe Ridge. And that probably means that plate forces obviously took over about this time, while before say 45 million years, the rift was actually magmatic generation, and magmatism was actually controlling the spreading rate until the rift got more mature, and then sort of plate forces took over from there on. Okay. So if we now look at a bit larger areas, so this is the Greenland-Iceland-Faroe Ridge we just looked at, and look at the North Atlantic and look at a couple of sections here in purple, sigma 3, which is over here. And luckily also we have got some ODP wells there, which gives us some geochemistry. Similarly for the Vuring margin section 1103, where there's ODP642, which has some geochemistry in it. And also a section here near Jan Mayen, which is this 700 line, which is this one. And then there's the conjugate margin of the Vuring Basin, which sits around here, which is on the Greenland side. So we can look at these velocities and sort of measure up like where the breakup is, what the thickness of the crust is at breakup here in the red line, what the sort of the magmatic unconformity would be, which is in this purple line over here, and then just a sort of random section here in black as the sort of rift develops. There you see these ODP wells as well marked. Similarly, for the Vuring margin, you can sort of depict breakup, which you can sort of depict from the velocity profile, because there's sort of a bend in the velocity profile and becomes much more higher velocities towards the right of the picture. Sometimes people explain this by stretching, but the velocities are so high that you need quite a lot of magmatism and you end up with very little normal crust to sort of make this work. So I think these breakups are probably pretty narrow and pretty close to where you find these step-ups of the velocity contours. So if we then look at the trace elements for Southeast Greenland, for the sigma line, then they all plot around here, very towards the lower side of almost close to more sort of compositions. But when we look at the Vuring margin, which is here depicted in US 104, these yellow lines, then we can see a clear trend from all the rocks, basically these are all seaward dipping reflectors, and they actually form an increasing trend, which means that you probably have increasing temperatures there. And something similar is found on the northeast Greenland side from some of the outcrop samples, but there's not enough vertical profile to say anything particular about it. But where the Vuring margin is, there is actually enough vertical profile to give some sort of an idea. And that's always the issue with these sort of profiles. We're very lucky to have the profiles in the Faroes and the central Greenland, because there's like 6 or 4 kilometers of stacked basalt flows. But when you just pick and choose some random samples, then those trends become much more blurred and more difficult to figure out. We also have a plot here for West Greenland, and basically something similar, but it looks more like a drop in temperature than anything else. These are the oldest formations, Bygad, and Nakalak is a more recent formation, as you see here in green. But again, not vertical sections, just bits and bobs of data that sort of is available from the literature. Now, if you look at the HVP diagram for the volcanic margins, same diagram, just different plots. And you can see here the sigma 3, which is the Greenland profile. And you can see here the Vuring margin, which is 1103, which is this one, this purpley one. And here you can see where the well was drilled, which is on top of this one. So basically you got a condensed section of all these seaward dipping reflectors, but an increase in temperature. It's about a 600 meter section basically. And most of these plot all basically on the passive margin, the volcanic passive margin trend, but some of them go a little bit out of it. Here, the Vuring margin, we don't get close to about high as 2, and some points. So it looks like most of them are just volcanic margin, or just passive volcanic margin, but some look like they have a little bit more going on. That's especially the case here for the Vuring margin. Western Greenland doesn't have any seismic. That's actually all the seismic lines are shot away from the core area, which sits over here. But there's a lot of outcrop data, and there's also a very significant unconformity between the Eocene and Paleocene layers, here depicted in red. So if we look at the West Greenland profile, we only have the geochemistry. So we see basically high temperatures when the famous picreds from the Bygad formations are deposited about 61, 62 million years ago. Then a rapid decrease. Then around this unconformity, we don't see much, but then in the Eocene, it's sort of the same as the Maligat and the Nakalak, the Svartinuk formations. But this unconformity is in between, and it might be that there's actually a drop there. It's just that we can't record it because there's not enough data basically. But it looks like there's a drop and then it picks up again. There's a bit more information on the Vuring margin, because we do have some geochemistry here depicted in purple, but also the red line is the seismic data. So we got a line all the way going to this Vuring spur over here. And basically we see some similar sort of trend that you've got high spreading rates here in gray, and that sort of drip sort of tapers off as the temperatures come down. There's just a couple of gaps because of this is a condensed section. I don't really have all the samples, and I don't know exactly what's happening because the younger sections obviously is not sampled here in this particular well. But what we can pick up from this section is that there's a breakup unconformity and a magmatic unconformity, and they look sort of similar to the Iceland trend, although the ages are slightly different. So it might not be that this is all created by the Iceland plume, but that actually you have a system sitting here by itself that has its own sort of merit, because these peaks are quite different than the one for Iceland. Now, if you then all put things together, you look at the geology here, and on the left is sort of showing where the sills are, where the breakup was, but going back to sort of breakup time. Jan Mayen sits over here. There's the Buring Basin. There's the wells that I just talked about. Here's the Greenland section with the Sigma line. You can see that there's a lot of pre-breakup basalt around Basalt, and also interpreted offshore and from this particular well here, the Brugden well in the Faroes waters, and a little bit onshore in Greenland, and it's the same sort of with Western Greenland and Baffin Island. And they look like there's sort of an area here. This is unfortunately all eroded, so you can't see much there, but there definitely seems to be a sort of pre-breakup basalt section over here, while the basalts going towards the north are all younger. This is a seismic lower crustal velocities, so looking at the velocities along those lines, basically these colors here so depict what the lower crustal velocity is, which tells you a bit about excess potential temperature. Excess potential temperature probably is a bit higher in this particular area, although there's only a couple of profiles, and definitely this area. But here there's very little information about wells, and obviously in West Greenland there's not much seismic at all. But similar things you can also see in the Buring Basin, that there is actually some elevated temperatures here, while the temperatures in between Buring and sort of the Iceland region are actually quite a bit lower. They have lower velocities, and so probably lower temperatures. So you get a high here, and you get a high here. And if you look at the basalt isopach, sort of look similar. So you got basically a high here, and also a little bit of a high there. And here the basalt isopach seems to be lower, and same with the lower igneous crust isopach. This is definitely a very clear high, and there's definitely a high here, but here it seems to all be a bit lower. So you seem to have different systems. I didn't talk much about the UK, but a similar system. So this system does not seem to be connected with this, because there's a northeast Rocco basin over here, which doesn't have any underplating or anything. So there seem to be sort of different sort of areas here in West Greenland, Iceland, perhaps here. That one might also be there, but is not so well constrained. But definitely the Buring Basin and the Iceland plume are pretty well defined. And the nice thing about the West Greenland one, although we don't have the seismic data, is that there's lots of onshore data. And basically that's what's sort of depicted over here. Here I just added up the basalt isopach with the lower igneous crustal isopach, and that sort of gives them an idea about the magmatic production or the magmatic crustal thickness. So then also added here are the pre-breakup volcanic transport directions from the hyaloclastite deltas, and that's pretty well defined in Western Greenland. They're all dipping away from the Baffin Sea, and if you go to the Baffin Island outcrops over here, then it dips the opposite direction. So there must have been a high or a volcanic plateau at breakup somewhere sitting here before the whole thing sort of broke apart. Similar, you can see a little bit here in Iceland. You can see dipping pre-rift strata that go towards the north, and in the deep wells here on Faroe Island, the Lopra well also shows this direction. Then there's also Simbrin breakup volcanic direction, which is basically when the rift sort of already sort of is generated, and those are here purple, also showing similar sort of setup as the green lines. But what is quite prominent from this picture is these highs here. There's a high here, there's a high here, and possibly a high there. And these are actually pretty much defined by the sediment transport direction. And if you if you saying that this is the breakup configuration just before breakup, give and take a couple of million years time, it looks like the sort of breakup probably started where the high was, and the rifts were sort of generated from the enormous high directions. Then at one point these rifts all ended up sort of connecting, and that's why you get the North Atlantic. Now there's been, of course, other models, and one is a recent one from Steinberger that uses a mantle plume that comes from eastern Greenland, and they use sort of the position of the Iceland mantle plume based on Torsvik here at 64 or 150 million years time. And these are sort of the thicknesses that they come up with in this model, where they use hot lithospheric flow just below the continent. And these are all theoretical values, of course, but the interesting thing about this is that there's actually a huge thick around Yamayan, in both cases, a little bit offset in this model compared to that model. But the data show actually that the Yamayan area is a bit of a thinning area, although to the south it's probably thicker, but this area is actually thinner. So, and also it doesn't show these particular islands over here that you have these particular centers. So if you use this model coming from eastern Greenland, then your thicknesses don't really add up. And so probably this model is probably wrong, because the mantle plume didn't come from eastern Greenland. It was all along in this particular place, pretty much from startup. So this is sort of an overview of the calculations. So early breakup temperatures from the geochem, early breakup temperatures from the seismic data, and what sort of temperatures you end up with. They're pretty similar, but you have to take into account that the error on the measurements is can be up to about 50 degrees. So it's pretty broad brush, but you can still pick up the trends, and that's the important thing: higher temperatures and lower temperatures. So here in Faroe Islands, the two different methods match very well, 200 to 180 degrees. I mean, that's pretty good. And so I think there's probably, using these two methods and using the geological record with the unconformities, makes this a much more powerful story than just using a bunch of ages and then start moving plumes around. So I think this is probably a better approach to sort of approach this. And you can sort of read this for yourself. And basically, I sort of come up with the idea at the end that there's probably different activities, although basically, obviously, the Iceland mantle plume is still present, but the plume in West Greenland probably died out about the Oligocene, and during, well, you've got the Yamayan still present, but it's almost completely dormant. But you can still see these images if you look at seismic tomography. There's definitely some feature there below Yamayan. So it might be that basically Yamayan is still present at the depth, but at the surface you don't see that much of it anymore. So this is sort of the model that I come up with, which sort of what happens for the North Atlantic. Initially, you got basically...
Max, sorry to interrupt. So we are running out of time. So if you can conclude in 5 minutes, it's okay.
Okay, so this is, well, this is the last slide anyway.
Oh, perfect, sorry.
There's just a conclusion after this one. Perfect. So this is basically just how it sort of develops. So basically you got a plume first, or a small plume, maybe not as big as people think, maybe only 500 kilometers diameter. Granitic magmatism and generating uplift, and the uplift creates basically the extension. So this is all magmatic generated, and all this is magmatic extension basically coming on, basically sort of similar to, say, Buck's model from 2070, or that was pretty simple. You got unconformities, so you got drops in temperature coming up and down, and that sort of generates the whole sequence basically as you go along. And that's basically along the hotspot track, and on the volcanic margins, basically the whole section sort of dies out about 45 million years ago. And then after that, it's basically normal ocean spreading. So these are the conclusions. You can read them at your leisure. That's about it. So thank you so much for your attention.
Thank you very much, Max. Sorry for the interruptions.
No worries. No worries.
That's really cool.